What happened?
There was this guy in a blog saying that. Is it recording?
Okay. Right, so as we said last time, or kind of half said, so I don't want to spend too much time doing boring proofs, so let's sort of jump ahead, and instead of proving these boring lemmas, let's try and use them. So let's just remember what they were first. So lemma 1 said that, I'll do the other different order, so x is at least 2 to the little OK, 1 minus mu to the t, mu to the L, beta over mu to the S. Lemma 2 said, thank you very much. So that y is at least 2 to the little OK, P0 to the S plus T times N. And lemma 3 said that S is at least, at most, beta over 1 minus beta times T plus little OK. Okay. We're actually going to need something a little bit stronger than this at some point, but you'll see when it happens. Okay. And then I'll change the statement to fit it. Okay, so just to, do you remember what everything is? So here, the final size of A is T. S is a number of density boost steps. And beta is the average size, suitable natural average, of the blue neighborhood in a density boost step. So. On average. Okay. Though in some sense it doesn't really matter for us because it's just there exists some beta that satisfies these two inequalities, such that these two lemmas are true, right? So actually, the definition of beta, once we prove this lemmas, doesn't really matter, except we're going to want it to be at most mu, I guess, right? Just,
Sorry, Rob. Right at the beginning, you said we should think about mu as being gamma, but at this point, it didn't appear.
Yeah. So far, we have not.
No dependency on gamma.
Yeah. So mu can be absolutely any constant between 0 and 1. So so for when gamma is constant, so for the purposes of all of these talks, mu is fixed and k and l are sufficiently large. But actually, the algorithm is more general than that. You can even allow mu to be little o1. You just have to be a bit more careful with your calculations. In particular, when mu is little o1, then these little ok's are going to matter more. So really, these should be little ol's when l is small. But yeah, I think just for simplicity, just think about mu as being any constant between 0 and 1. Okay. Right. Okay, so let's try to prove that. So if gamma and delta are sufficiently small, constants, then the Ramsey number KL is at most, so what is gamma? Just remember, So gamma is L over L plus K. Okay? So gamma being sufficiently small means L is a small constant times K. Okay? And delta is a small constant, then we get an exponential improvement over the Eddy-Seckerish bound. Okay? So for this, we're not going to need any kind of like complicated computer program stuff, simulations. It's going to be very simple. Okay? It's going to follow in a very simple way from those three lemmas. Okay? And then you'll see perhaps once we do the calculation how, okay, we're being wasteful in various places. If you optimized everything, then these things wouldn't need to be so small. But the optimization is just, it's boring, right? It's just a sort of standard optimizing calculations. And then it gives you something, and you can, the computer will tell you what it gives. Okay, so what's the proof? Okay, so we're going to be given, so let's let n be Ramsey KL minus 1, and let's consider a coloring with no red KL or blue KT. Some red under here. It's just definition, right?
No, I mean, you want to have this proved by implication.
Don't think so. Yeah. I mean, right. So. Okay. So no. Maybe there will be contradiction then. Maybe there will be. Yeah. Okay. But so far not. So far, just define n to be this. You got a coloring. Okay. So your first thought might be, right, we should apply the book algorithm, find this big red book, and then see how big our book is.
In this asymmetric set, we have to be careful about the density.
We have to be careful about the density, exactly. So the first step is like, okay, first question is, so what if the red density of chi is too low? So right, so what does too low mean? What would we expect or like the red density to be? 1 minus gamma, exactly. So particularly if it's less than 1 minus gamma minus, let's say, delta.
Not the same delta.
Actually, let's say the same delta. Really what I mean is 1 plus delta times gamma. Right, so smaller by some small positive fraction of gamma. Okay, so what should we do in that case? Yeah, right, so this is saying that if we were just at Eddy-Seckerish, we saw this, we'd be like, oh, good. We can take a blue step, and we've gained a factor of 1 plus delta. So we've improved this by a factor of 1 plus delta. And if we do that L times, we just keep going until we hit 0, then we've improved by a factor of 1 plus delta to the L, which is basically this. Right? So, okay, to be pretty precise, this is not actually delta, it's like 2 delta or delta plus delta squared or something, but whatever, let's just put delta here. Okay. Right, so then take blue steps, blue Eddy-Seckerish steps, until the red density is good.
Or, oh, we don't have to know, we can finish it by.
So on each step, we don't use the low density, but we use the fact that there is at least one vertex with
Exactly.
Low red degree.
Exactly. Yeah, so right, exactly. To do the red book, we just need good density. To do the blue step, we just need one vertex of high blue degree.
Sorry, Rob,
So we're going to use these blue vertices, right? So what do? So we get some vertices v1 up to vm, say, right? Such that the common blue neighborhoods of these guys is how large? It's at least 1 plus delta to the m times, so I don't want to put gamma to the m, because gamma's changing, right? Gamma at the beginning is L over L plus K, but after one step, our gamma changes to L minus 1 over K plus L minus 1. So what it really means is, right, so our gammas going to have to vary depending on how many steps we take. Yeah, so the corresponding thing for gamma is, it's L minus I, K plus L minus I equals 0 up to m minus 1 times n. Okay, so every time we get an extra factor of 1 plus delta over the current gamma, which is this guy, then we can take a blue step. And when we stop, so we keep doing this until, so either the maximum blue density, the maximum blue degree is so small you can't do this anymore, or weaker, the red density is what you want. Until, so let's call this thing U. The red, we'll call it UM. Density in UM is at least 1 minus 1 plus delta times gamma prime, where gamma prime is L minus M over K plus L minus M.
Couldn't you do something like by induction on L or something, and then if you do one blue step, you already have proved by induction that you have like exponential.
But then you have to do base case, right? And I guess this is the base case.
Yeah, right. Yeah, so what, yeah, exactly. What is your, yeah. Is there a way of stating it like that? Yeah.
The base case is trivial if you take like delta really small.
Or even constant, right? I mean, you could get to constant, and then for constant you don't care about what you get. Right, it works.
I don't know.
Yeah. It looks like you might be able to write it like that. I can't quite see how to do it. Yeah. But anyway, so we can take these blue steps. We get to some point. We've won this factor of e to the delta m. And so if we can prove it for L minus m, right? If we get e to the minus delta times L minus m, then we're happy. Because note that. So why is this the correct thing? Note that k. So this thing times, so k plus L, choose L, times this product, I equals 0 to m minus 1, L minus I over k plus L minus I, equals what? We're just knocking off a bunch of these guys. It's k plus L minus m, choose L minus m. Right? So this term is exactly changing this thing by the right factor, and this 1 plus delta m is just exactly what we need to gain as L goes further away. And all we end up with L minus m instead of L, which is further away from the diagonal, so our gamma has just got smaller. You might complain it's not constant anymore, and we want k and L to be large compared to this constant, perhaps. So if you're really worried about that, you can just say, well, look, if m goes so far that L gets tiny, you've already won, basically. You could change this to a 2 delta if you like. and you're winning by twice as much as you need in each step, right? I mean, I can even do that if you want. Does it? I don't know. Yeah. Right, so if this goes on for a really long time, you've already won. You can just apply a de Seceres, and life is good. Okay, so we can assume that we haven't gone too far. Okay. Okay, so that's the first step. So we can basically reduce it to the case where our red density is close to what it should be.
Just to put in a quantitative,
Yeah.
how much we're talking about, like linear in L. If we get to linear in L in M, then we're done. But otherwise,
Yeah, if M is,
too far.
yeah, right. So M only needs to be L over 2 or something. Yeah. Okay. So I put 2 delta. M just needs to be L over 2. Yeah. 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 I guess in the paper we're more careful because we care about the constant you get. Here, anything works. Okay. Yeah, so in the paper here we do care about the constant, unlike other places, because then we need to plug into the other part of the argument. We'll talk about that later. Okay. Okay, so we've basically reduced it to the case, so now, okay, based on this, we can just assume that we had what we wanted. So maybe I'll return to, let's pretend this didn't happen. So M is 0. So now we may assume M was 0, and so the red density in chi is at least 1 minus 1 plus delta times gamma. Okay? Just to simplify the notation, right? We didn't lose anything. Okay, I'm going to apply the book algorithm. To chi. So really, the book algorithm's input is a set x and y, right? And apply it to sort of a random bipartition, equi-bipartition. So in particular, we want that the red density between x and y should be at least this guy. Which should be P0, should be at least 1 minus this guy. Right? Okay. And so why does such a partition exist? So we definitely don't want to lose a factor of 2, right, in the density. Yeah.
Just like the expected value of the density is that, so it exists the partition.
Yeah, so
That's where
You do that, you lose a 2, right?
No,
The
no,
expected
It's one vertex and the rest. The density is at least, so you have one vertex with at least that.
yeah, but we want an equipartition. We want both to have size n over 2.
so this doesn't work. Like the expected value over all the partitions of the density is at least that.
Yeah, right. So each, and what's the easy way to see it? Each red edge has a certain probability of being in, which isn't exactly half, but it's close to half. Each blue edge has the same probability of being in. So the expected number of red and blue has to be whatever it was in the beginning, right? Just yeah, the expected number is what you. Yeah. We're not throwing things away, right? So this is just the expected density. Yeah, exactly. Okay. Right. Okay. What I have to say is we have to pick mu equal to gamma. Okay. Right. Come back over. Maybe I'll leave the statement. Okay. So, what do we need to do? We need to show, so we're going to end up with, so this gives us a book, AY. Right? A is going to have size T by definition. So what do we need for Y? We'd like Y to be big enough that we can finish the argument, just with edge separation. So we need Y to be at least K minus T plus L, choose L. Yeah. So I'm assuming M is 0. So really this is an L minus M and an L minus M. Yeah, let's not make our lives more complicated for no reason. Okay? Okay, so this is our aim. If we can do this, then we're happy. Right? Because then we'll have either a blue book, a blue clique of size L, or a red clique of size K minus T by Eddy Sekeresh. Add it to here, this, we get a red clique of size K.
So, like in Joel's suggestion of
Yeah.
reduction, why can't you use your Bible there to get
So that we can, for sure. But the improvement that you got, I mean, yeah, it would be as a function of L minus M, I guess. Oh, sorry, here would be a function of L. So yeah, so you would get something a bit extra.
What do you get, like, e to the minus K minus T, basically, like, do some constant?
You'd get something like e to,
Smaller than L, right?
sorry?
K minus T now is smaller than
Well, it depends how small gamma is. And we haven't yet said how large T is.
Yeah.
We're about to say how large T is.
Okay.
Yeah. So potentially get something, but actually, right, in practice, once L is small, this is moving you closer to the diagonal, and therefore your constant's getting worse. So you can do it, but yeah, it gives you something, but yeah, perhaps not enough to be worthwhile. Right, so yes, if we get this polymath thing going and actually really want to optimize everything, then yes, we want to do things like that, for sure. Right. Okay, so we want T to be big. Right? Basically, for us, the bigger T is, the better, because then this lowers this bound on Y. So first lemma is going to be that if n is at least e to the minus delta L, K plus L choose L, and gamma and delta are small, then T is at least 2K over 3. Okay? So then we do not run out of vertices in X until T is big. Right? And this is whatever beta we choose. Or whatever beta our enemy chooses, I guess I should say. Right? Yeah, so this is, I mean, perhaps it's the first surprise, but it's
Have you chosen mu yet?
yes, so mu is here.
Mu is in.
Yeah. Thanks. Right, so when we were, I mean, so in Thomason's conjecture about books, and when we were starting to think about this, we were thinking about taking just T to be some very small constant times K, and trying to get Y to be really like 2 to the minus T times what it's supposed to be. It's actually happening something very different, right? We're getting Y is going down by 2 to the minus T times 2 to the minus, or whatever, P0 to the, no, this S, we're losing this P0 to the S factor, right? I guess over here, so I should be pointing. Right, so we're not getting P0 to the T, we're losing this extra P0 to the S, but on the other hand, we're getting T that's really pretty big. Yeah. Right, as you see, if L is smaller than K over 4 or something, like even K over 3, yeah, sorry, you don't have to, I'm confused with gamma. Yeah, if gamma is less than a quarter, Yeah. Thank you. Yeah, if L is less than k over 3, then you're not getting past it, right? You're just going towards the diagonal. And so you're left with something where it's harder to deal with. Yeah, the nice thing about these steps is they were making our life easier. They were taking us further from the diagonal. But this is moving us closer to it. OK, so how are we going to prove this? Well, we have a bound on x. We run the algorithm until x disappears, or at least it's till size 2 to the little OK. So really, we're just looking at when this thing is 1. Right? OK. So we want to look at, so proof, we know that 1 minus mu to the t, so, and mu is now gamma, 1 minus gamma to the t, gamma to the L, beta over gamma to the s, times n is at most 2 to the little OK at the end. OK, let's set it equal. Maybe, sorry, I'll just say at most. Right? Because x is at least this, and at the end, x is at most is 2 to the little OK. And this is clearly giving us some lower bound on t, right? In terms of beta and s and gamma and these complicated things. Like how are we going to deal with this horrible expression on the left? Well, you know, we're used to dealing with things like that, right? Not too complicated. You just have to simplify in the right way. Yeah, so it looks a little bit scary, but really it's not. OK, so what's the first observation? Well, here's this s. We have an upper bound on s. Right? So what do we have? Let's look at beta over gamma to the s is at least, right, because s is at most that, and beta is at most gamma, because gamma is mu. Beta over gamma to the power beta, sorry? Thank you. Beta t over 1 minus beta plus little OK. Now, the first thing I do, I don't like this 1 minus beta. It looks complicated. But beta is the most gamma. So I can replace it by a gamma. OK? Could also do that with this beta, but I don't want to. That one's important. OK? OK. Now let's look at this first term. Let's forget the little OK for now. We have a beta to the beta, and then a bunch of other stuff. OK? So what can you tell me about the function x over c to the x? When is that minimized? How do you make that function as small as possible? This is an important inequality in combinatorics. This is one I use a lot. Yeah, so whenever you simulate this, it's always when the thing inside is e, or 1 over e in this case. So I guess, yeah, if I want to say instead what c over x to the x is at most, you put the thing inside equal to e, and so x is c over e. I mean, you just differentiate, right? And something comes out. It's that. Right? So this happens a lot, right? You get something that looks like this. Right? So the thing we have is, OK, so what's our situation? We've got a beta over gamma to the beta. When is that minimized? It's minimized with beta over gamma equal to 1 over e. Exactly. Thank you. Check everyone's awake. OK, so what do you get? You get e to the minus gamma over e. Is that right? OK. OK, so let's go up in here. I'll get rid of this thing. What do we have? Exp of minus gamma t over e 1 minus gamma. And then we got this little OK, which is a bit annoying because we didn't take into account when we were maximizing here. And beta over gamma can be as small as like 1 over k or 1 over k squared or something. So that could actually kill us. So actually we need something better. So really I want to put 1 k to the 1 minus some small constant. So over here, when we prove this lemma, which we didn't, we really want a k to the 1 minus c. And the purpose is just to beat this annoying beta to this guy. Okay? And it's true, and it falls from the same proof. Sorry.
Sorry. You said something that was like 1 over epsilon times log k or something?
So, right, yeah. So what is it? Where did this come from? So there was a log k over epsilon in there. So that's fine, because epsilon is like k to the minus a quarter.
Yeah.
But there's also, in the proof at least, something like an epsilon times k. Actually, I think maybe what we actually prove is like epsilon to the quarter times k or something stupid. But epsilon is also, it's k to some power, so it's fine. Right? Maybe it's epsilon to the half, I forget. Yeah, this is really just because we're dealing with these stupid big steps in a stupid way. Yeah, because we don't want the shrinking of the world to mess up our, yeah. Yeah, so there's some, I mean, okay. Okay, perhaps I shouldn't claim too much. Yeah, I don't know what the correct error term is here. Yeah, for the very far off the diagonal argument, which I'm supposed to be currently writing down, you need to be a little bit more careful here, but actually not much more careful. Yeah. Okay, so really this is just this, and then because we got k to the 1 minus c, here we can now put a little OK. Forget about it. Okay. Right. Okay, so that was easy. And that's actually like the worst part taken care of, right? The rest of it is simple. But first of all, let's put a note here that this was putting beta to be gamma over e. Right? So I'm not claiming that this is the worst beta for us overall. It's the worst beta for this step. Right? Later on, there'll be a different worst beta for a different step. And in fact, neither is really the worst beta is somewhere in between. Okay, so we're being generous here. We're saying, for this part, you can have the worst beta you like just for this step of the argument. Fine, we'll give it to you. Okay? Okay. Right. Okay, what next? Okay, we've got these horrible, like, 1 minus gamma and gammas. And we've got this n. So here's a nice fact. So what's n? N is like k plus L choose L times something small. So let's try and rewrite k plus L choose L as something that looks a bit more like this rubbish. And the nice fact is that up to some error term that's actually very small, it's way, way smaller than this. This is basically gamma to the minus L 1 minus gamma to the minus k. Okay. And you can sort of see this by just thinking about Erdős-Ekerés proof. If you just take L steps of size gamma and k steps of size 1 minus gamma, that's where you end up. You can also use Stirling's formula, right? So k plus L choose L is k plus L factorial over k factorial L factorial. So what's this basically? It's like k plus L to the k plus L over k to the k times L to the L. The factors of e disappear, and there's some polynomial factors that go in here. And then this thing is, what is it? It's k plus L over k to the k times k plus L over L to the L. I didn't really have enough space for that. Right, and that's 1 over 1 minus gamma, and that's 1 over gamma. Okay, so nothing happened.
We don't need to be careful with these factors of 2 to the little k because we're fighting again.
Yeah, we're always going to win by 2 to the constant k. Right? L is constant times, yeah. Yeah. Constant times k. Okay, so maybe we can get rid of this. I'll just recall what P0 was. I'll leave this here. And mu is gamma. Right. Okay, so if we now just plug things in over there, what do we see? The gamma to the minus L cancels with the gamma to the L. That's great. And we have a 1 minus gamma to the k minus t, or t minus k, or whatever. Okay, so what does this imply? 1 minus gamma to the t minus k, thank you, times this ugly term here, minus gamma t over e 1 minus gamma, and then there's a little OK term, is, thank you, and the e to the minus delta should be at most e to the delta L, basically. Yeah. Right, I'm ignoring little OKs. I mean, they're much smaller than this guy, right? Yeah. Okay, right, so we're still slightly knowing we have this 1 minus gamma instead of an e. Okay, well, let's use the very advanced inequality. 1 minus gamma is at most e to the minus gamma, right? Which is not a regular inequality when gamma gets big, but is, I mean, we're taking gamma small, so we don't mind. And actually, we don't mind all the way up to like gamma is a quarter or something when we start caring.
Don't you want like to lower bound that thing to get a bound? Because you need to
Yep.
stop when t is.
Yeah, so we are going to stop at that point. So x is at least this. So when we end, x, we know x is at most this at the end, right? So we know that x is this size at the end, and x is bigger than this. So at the end of the algorithm, x has size 2 to the little OK,
Yes.
and that's bigger than this, right, by the lemma. Yep.
The direction of this inequality here is an
Oh, right. So notice we have 1 minus gamma to the, where are we? T minus k, right? So actually we're going to use 1 minus gamma to the minus 1 is at least e to the gamma.
Okay.
Yeah, we're going to go the right way around. Yeah. So what do we get? And now we take logs, and we get gamma times k minus t minus gamma t over e 1 minus gamma is at most delta L. Is that right? Yeah, so now let's divide by gamma, right? Divide by gamma, because the gamma is kind of getting in the way. L over gamma is what? Gamma is L over k plus L. So L over gamma is k plus L. So delta times k plus L. I mean, it's basically delta k, right? Okay. And now what? And gamma's getting small. So 1 minus gamma is basically 1. Yeah. So this, I mean, also erase this 1 minus gamma, just because gamma is small if it's close to 1. In fact, okay, so this is going to tell us how large we can take gamma, basically. But I'm going to erase it for now, just so you can see that this is saying that k is at most 1 plus 1 over e times t plus delta k, basically. And 1 plus 1 over e is bigger than, smaller than 3 over 2. Smaller than. Smaller than 3 over 2, because e is bigger than 2. using this fundamental fact from analysis. Okay? Okay, so because E is bigger than 2, we can afford, if we take gamma small enough, then we're fine. I can replace it by a 2. Right. Okay. Okay, and take delta small, and you get T is at least 2k over 3. Okay. Right, so the limit of this argument as gamma tends to 0 is k divided by 1 plus 1 over E. Right, so you can't get it better than that. Okay, so we can't hope to get 3/4. Okay, but we can get 2/3. Okay? Okay, good. Everyone happy? Cool. Okay, now let's try to bound Y. Okay, so how large is Y? So now Y is at least, so 2 to the little OK. What was P0? It was 1 minus gamma minus delta gamma to the S plus T times N e to the minus delta L k plus L choose L. Right. So using our lower bound on P0 and using our assumption that N is large. Right. Okay. Right, so how are we going to bound this guy? Sorry? We need an upper bound on S, because this is less than 1. Yeah, so it's okay. It goes the right way. Yeah. Right. Okay, but we're not comparing it to k plus L choose L, right? What are we comparing to? We're comparing it to k minus T plus L choose L. So we need to note how k plus L choose L compares to k minus T plus L choose L. Right. I don't know if you really want me to calculate this, but it's basically, so error term, when you increase T by 1 at the beginning at least, you multiply by, so k plus L minus 1 choose L over k plus L choose L is what? It's like 1 over k plus L times k. Right? So you're losing a factor of 1 minus gamma each time. So you can expect a 1 minus gamma to the T or minus T? Minus T, I guess. Right. But there's also an error term because we're doing this T times and it's changing, right? It's not going to be K anymore. It's going to be, so if you do minus 2 over minus 1, you get a minus 1. So things changing very slightly. So you end up with an error term with the form e to the t squared over k or something. Oops. Except the constants matter, so let me cheat and look at what the actual inequality is. And there's a gamma, which is also kind of important. Gamma 2. Okay. So if you just write out what these things are, approximate them in a very simple way, it takes like 3 lines, you get this. Okay, so no big deal. Okay. Okay, so this is a win, right? It's really plus. It really is plus, right? So this is a win. These two things are kind of fighting against each other. And then what the fight is between is this 1 minus gamma. Let's forget this. This is small, right? I might just delete all the deltas, right? This to the S is fighting with this guy.
Sorry, Rob.
Yep.
We need the 1 plus delta times gamma at the beginning again. Just because we need it to win, right? So
Yeah, we wanted to win in every step. So, but if we don't mind delta being very small, so first what I'll do is I'll do it without delta, see that we win by some actual constant, and then observe that if you let delta be sufficiently small, you still win.
Okay.
Right? Because the deltas, I'm going to win, without the deltas, I'm going to win by some actual constant. And so this is going to be, I mean, what's the difference? It's an e to the delta gamma k. This is an e to the delta L. Gamma k is L. Right, so it's really, if we win by some constant L, then we're fine. Okay. Okay, so what do we need? What do we want? We want 1 minus gamma to the s, right? The 1 minus gamma to the t is killed by this guy, times e to the gamma t squared over 2k to be bigger than e to the something like delta L. Right? Big enough to beat these other guys. For some maybe delta prime, some absolute constant. Shall I give it a different name? Small constant. Okay. Okay. If this is true, for some actual constant, just take delta small enough and you win. So, is this true? Well, what do we know? We know that S is at most, beta is at most gamma, so it's at most gamma over 1 minus gamma times t, plus little ok, who cares? And t is at least 2k over 3. So I claim we win by miles. Because what this is like 1 minus gamma to the s, so 1 minus gamma to the s, is at least what? It's like e to the gamma s, gamma small. So we like get an e to the gamma squared t. And gamma small. And this term, e to the gamma t squared, is at least, that's just 2/3, right? So you get something like e to the 2 gamma k over 9. The point being, here we have a gamma squared, and here we don't have a gamma squared. Here we have a gamma. So this one's much bigger than that one. Right? So we actually win by some constant times gamma k, that is some constant times L. Right? We'll put a gamma k here, maybe it's. Right. And that's it. Right? No difficult computations, just approximate stuff.
So delta and gamma, it's better to have delta and gamma having the same order.
Yeah, they can have the same order of magnitude, yeah, exactly. So in fact, the version of this that we prove in the paper is gamma is at most 1/5, and delta is like gamma over 20 or 40, I forgot. Maybe the first version, sorry, is 10, whatever, something like that. Right, whatever.
There's a minus missing in the first.
Thank you. Okay. So that's it. That's how you do it. Okay. So right. So now suppose you want to push it towards the diagonal. So one thing you can do is just first you can tighten up these calculations and you get something like this, and then you tighten a bit more and you get a bit further. At some point you get stuck unless you really estimate properly, because we were taking, remember, beta to be gamma over e here, Whereas when we're bounding S, yeah, we're bounding S, then all we're using here, this one, oh, sorry, it's here. We're only using, here we're using beta as gamma, right? Not gamma over E. And if it was gamma over E, we'd gain something here. Right? So at some point, your gamma gets big enough that you start running into this is an obstacle. Okay, so then we have to do something a little bit more careful. I'm not really sure how much it's worth saying about this. Right, but yeah, so if you just do this calculation but do it more carefully with a computer, or I mean, not even with a computer, you can do it by hand and you end up with some function, right? So do I want to explain this? So I want to claim that, maybe the diagonal case, over n is at most the maximum over x and y in some range of two functions. You're staying upstairs with a sauna, but here is similar. No? Ah, it's on. Are you not warm? Just because I'm running around, I guess. I should. Okay, if it gets too cold, then complain. Right, where this guy comes from the size of x, other way around, sorry. And this from the size of y. Anyway, let's just see. Right, so what is f? Let's do the lemma and see. So, right, I'm going to claim is less than something. And how am I going to do it? Okay, I'll tell you what it is once we see. What am I saying? So I just want to consider the size of x first. So we know that the end of the algorithm, yeah, so let's let n be the Ramsey number minus 1. Consider a coloring and with no monochromatic kk.
Sorry, Rob.
Yeah.
The previous proof with this theorem for our
Yeah.
diagonal, we assumed n was rk minus 1, and how did we actually found the book? As much as we wanted.
Yeah.
And then we found either read k minus t in the
Right.
which we assumed we did that, so this is a continuous summation.
Yeah, so all of this was assuming, yeah, perhaps I should do that. That's all right. So this is telling us, what this told us was that at the end of the algorithm, A has size t and y has size at least k minus t plus l, choose l, for some, yeah, we don't control t, but whatever t is, we get this. Okay, and that implies, because we have this red book, we're going to get a pink book, because my red is over there somewhere. and y. Right, now inside here. So this is under the assumption that n was at least e to the minus delta L, k plus L choose L.
So no contradiction at all. We don't need to assume that. We just found our
Right, and this was R choose KL minus 1, right? So yeah, we're... Sorry?
Just put RKL and you found the red click or why do you need this contradiction?
When we're running the book algorithm...
Either we find them or we're done, or
Yeah.
we found them here. So
Right, yeah, if you state it like that. Yeah.
no contradiction at all.
Yeah. Yeah.
It's a beautiful algorithm that finds you a red click.
Yeah. Yeah, it's sort of convenient when you're stating lemmas to not have to say every single time either you find a red clique or a blue KR or whatever. But yes. Okay, so it's fine. Cool. Right, but here actually then we do need to take n to be this. Right. Sorry, this is over k. What did I write here? Sorry, I wrote the wrong thing here as well. You did not correct me. That would have been.
Just repeat the definition of f and g.
I have not yet defined them because, sorry, yeah, I should have made that clear, because I've forgotten the definition, so I don't want to get it wrong. Yeah. Yeah, it will fall out of the proof. Okay, so we're going to use the book algorithm to bound the Ramsey number by some weird function, and it's going to be the worst case over x and y, in some range. Okay, so how are we going to do it? So we take n to be Ramsey minus 1, take some coloring, assume that red is more common than blue by symmetry. Okay, so assume the density in red of chi is at least a half by symmetry. Okay, and apply the book algorithm to a partition xy such that the red density between x and y is at least a half. Okay, so we pick some equipartition again, do it randomly, the expected density is at least a half. So there exists one, run the book algorithm with mu equal to, well now gamma is a half, and that's not very good for the book algorithm because now our density boosts would then only be of size, of relative size 1, so our bound on S would only be t. And that is very bad for us. We definitely do not want that. So instead of taking mu to be to a half, we take it a little bit smaller. Take it a little bit smaller, it forces this to be a bit smaller, it makes our S a bit smaller, and we don't lose too much otherwise. And it's not very sensitive, 2/5 is fine. Okay. Again, if you really want to optimize things, you want to take the correct mu. I do not know what it is. It's something close to this, I think. Yeah. Yeah. Okay. Yeah, I think it's sort of delicate enough that relatively small changes here could make a relatively large difference to the final constant you get. But yeah, one has to be careful. So perhaps you'll see later, yeah, exactly what I mean. Okay. So what do we get? So look at the size of x. X.
No, our P0 is
Sorry?
our P0 is 1.5.
P0 is a half, yeah. I mean, okay, officially P0 is this guy, but whatever. Let's pretend it's a half. Yeah, it's at least a half. Yeah, okay. Don't want people to be confused. Okay. Right, 1 minus gamma to the t. That's 3/5 to the t. Gamma to the L, 2/5 to the L. And then beta over mu to the S. Mu is 2/5. Sorry? Yeah. to the s, right, times n. Right. And we know at the end, this thing is choose little OK. Right. So now if we take logs, and this guy's Ramsey, right? This is, actually it's n over 2, right? It's n over 2. So this is basically Ramsey of k over 2. So let's take logs. So this tells us log to the base 2 of Ramsey, this guy, is at most t log to the base 2 of 5 over 3 plus, now what do I want to say? Right, so now I want to deal with beta. Beta is at most 2/5. We also know that S is at most beta over 1 minus beta times t. So what does that tell us? So it also allows us, yeah, so perhaps I should do it over here. Right. So let me ignore this term because it's not going to matter. So we'll invert this thing. So it's, let me do it over here. So S is at most this, I'm just going to invert it. So S is at most 1 minus beta over beta times t implies that, thank you. Thank you. Didn't want to invert that. S times 1 minus beta. So 1 minus beta times S is at most beta times t. Pull the beta across. S is at most beta S plus t. Beta is at least S over S plus t. Right? Okay, so just inverting, like baby algebra. Right, so we get an S plus t, an S over S plus t here. So, yeah, sorry, I'm going to have an L log to the base 2, 5 over 2, is the other side, and we're going to have an S over S plus t, so plus S log 2s plus t over 5s plus little OK. Right, so just some simple calculation. And that is our f. So, except I want to divide by k. So we have a t over k, which I'm going to call x. Okay, so t over k log to the base 2, 5 over 3, plus L over k log to the base 2, 5 over 2, plus S over k log of base 2 of 2s plus t over 5s.
What is L now, since we are estimating?
Thank you, it's k. Thank you very much. I was like, I don't remember this L being here. What is it going to happen to it? It's k. Thank you. L equals k. I assumed it would just work, like something would happen I'd remember, but thank you, something happened. Yeah, thank you, it's k. Okay, so that's so what's f? F is Yeah.
So the variables are t over k.
Oh, sorry, g is that. Sorry, not g. Sorry, so it's x log to the base 2 of 5 over 3 plus log to the base 2 of 5 over 2 plus y log to the base 2 of this nonsense. So this also cancels, so you get 2x plus y over 5x. Okay? So it's just some function of two variables.
Over 5y, right?
Y, thank you. Thank you. Okay? So just some silly function of two variables where x and y can go between 0 and 1. And, okay, they have to satisfy this inequality, right? So y is at most mu over 1 minus mu times x, whatever. Okay, so that's the world. And then f is a bit more interesting. So another inequality. Can get rid of this. Can do the same thing. Except now we're going to look at y instead. Here we just get p0, which is a half, to the s plus t times n. And we take logs again. This is Ramsey number. And this time it's very simple, right? You just get s plus t. Am I talking nonsense? Sorry, y is not equal to this guy. Yeah, sorry. Y should be at most Ramsey k minus t L. So I won't do it quite yet.
Where L is k.
Where L is k, thank you. L is always k for this few minutes. Yeah, thank you. Right. Because we chose n to be this guy, we chose a guy with no monochromatic kk, we know that y must be at most this large. Right? So it's this thing. So what am I saying? S plus t plus log to the base 2 of Ramsey k minus t plus little ok. Right? So we have a bound on diagonal Ramsey in terms of off diagonal. Right? Okay, so most t k minus t over k plus x plus. Sorry? Sorry?
Just swap the order of
These guys?
Yeah, I mean, I know they're the same, but morally.
Is there a moral here? Yeah, so right, so then this guy is, is log of, whatever, Ramsey k minus xk k plus x plus y, basically. Yeah, and so whatever bound you get here, you can plug it in, and then you just need to maximize this thing over x and y, right? And that's where these pictures come from, with the region that you arrive in, the region that you win, and if they're disjoint, it means that the maximum over these two is less than 2 minus delta.
And you can't just apply the bounds, the non-diagonal, off-diagonal bounds in this guy, because you can guarantee that it's actually not off-diagonal.
Right. So
We don't have
yeah, this is So whatever f is really is just whatever bound we plug in here. So if you plug in a Sekeresh, you get something, and then it's actually bigger than 2. So the bound is 2 plus delta. But if you
2 minus delta, but not 4 minus delta? 4 because it's longer. Yeah.
Yes, 2 to the 2. Yeah, 2 to the 2. Yeah. Yeah, but if you plug in this slightly stronger bound, then it's slightly smaller, right? So whatever improvement you get here kind of corresponds to an improvement here.
Yeah, but if you can't guarantee that it's off diagonal, like, can you guarantee that this k minus t, can you guarantee that k minus t is smaller, or the gamma relative to this is smaller than 1/10, for instance, so that you can apply this?
So no, you can't. But let me say what you can guarantee. Yeah, so that's a good question. Let me draw the picture. Okay, so first let's bound Ramsey r minus tk by using the Eddy-Checkerish bound. So 2k minus t, choose k minus t. Okay. Then we can draw a picture of where g is at most 2 and where f is at most 2. So where g is at most 2 looks like this. I'll color it in blue. So this is the region where gxy is at most 2 if n is, let's just say, 4 to the k. Right?
Don't you mean like greater than 2? So that
Sorry, there's no 4 to the k here. Yeah, sorry.
Don't you mean like greater than 2 so that it fails in this region?
Yes, I do. Thank you very much.
Isn't this the success region where this is
No,
less?
it's
the end.
Thank you. I do mean it's at least 2, right? So let's just check. This is increasing in x and increasing in y. So yeah, if it's over there, it should be bigger. Thank you. Right. And then you can draw, oops, it doesn't go down that fast, because it wants to get down here. This is the region where f of xy is at least 2. Thank you. Right. So if, and I misstated the theorem, that's why it's not making any sense. I mean, what does the max of this over xy mean? Well, I don't mean that. I mean, what do we prove? We prove that this thing is at most f for the worst guy, and it's at most g. So it's the min of these two. So let me get a bit more space. So most, the max over x and y of the min of these two guys. Yeah, so you just need one of them to be smaller. Thank you. That's okay. Right.
Also,
Okay.
x and y are not arbitrary numbers. They have to satisfy some condition.
They do. It turns out that condition actually isn't a big deal. It is. It's not a complete. It uses at some point, but it's not such a.
So it doesn't help. It's something that can help us at this point. But
Yeah, it could help us if we wanted to, but actually, yeah, we don't really need it. It's sort of it's up here basically, and they're already kind of they're already disjoint by that point. Right. So if we are wherever we land somewhere here. Right. We get some t and some s. Here we're not in the f range, so the minimum of those two is less than 2. So we're happy. Similarly, if we landed sort of over here, then they're both less than 2. If we land over here, then g is less than 2. The only place where we're not happy is here, this intersection. If we land in there, then they're both bigger than 2, and we've lost. But what is this range? So this range is, this is sort of, x is roughly 0.8. So it's all between 0.75 and 0.85 or something. And s is sort of roughly 0.45 or something. Okay? So in this little sliver here, we know we're only in trouble when when t is this large. T is like 4k over 5. So we...
This is for English estimate.
Right. So eddy securation is enough unless t is in this range and s is in this range. Only if you land here, eddy securation is not enough. In that case, so it's only in that case, in this range, that we need the improvement. So it's okay to only improve it when so we do RKL is at most e to the minus, so what we actually do is like L over 50, something like that, K plus L choose L, right, if L is at most K over 4. Right. So when L is at most K over 4, it means that we're sort of to the right of somewhere like here. This is like x is 3/4. Corresponds to that point. And so there we say, here actually we get this jump where we go to our bound, and then the whole way up, oops, we get something a bit better. Right? Yeah, so we don't need to improve it down here, which is the close to diagonal range. We only need to prove it beyond this point, and luckily that's the only dangerous bit. Yeah, so if you look at the pictures in the paper, if you have very good eyes, you can see a little jump at 3/4. Yeah. So that's why. So we're using eddy securation in this range and using our bound just beyond 3/4. Yeah. That's where the little jump comes from. Yeah. Okay?
So that's it.
And it also has a jump
Yeah.
in the blue part because...
No, the blue part does not jump because it doesn't depend on the Ramsey number.
True.
Yeah, the blue one is it's a very simple function. It's just,
So
yeah.
this, for me, more evidence that if you iterate this for the lower ranges, then you should get something even better, right?
You will definitely get something better. Yeah. Yeah, I don't want to promise how much better, but I think it's worth figuring out, right? So I think that, this should be pushed as far as it will go, and we'll find out what constant we get, and then that's the new mark to try to beat. Yeah.
So we kind of run the book algorithm twice, once for one color and once for the other color.
So here we're actually just running it once,
Yeah.
but here we're just looking at how large x is, and here we're looking at how large y is.
But for estimation of y, we run it again, right?
Sorry, to get this bound.
Yes.
Yes, right. So yeah, let me draw a picture. Thank you.
And the colors are swapped.
And the colors are swapped. Exactly. Yeah. So let me draw this picture. Yeah. So this is a sort of picture of the world of K versus L, and here is K versus K. And so we run this algorithm, and we get down to a point here, which is something like K over 5 versus K. Right, so red is now, we only need K over 5 more. So this is what this means. And now, you're saying, okay, now we're off diagonal, but now we want to do blue. And so we do blue for, don't know, like 2/3 of K, something like that. Something like K over 5 versus K over 3. And then here we apply eddy securation. Yeah, exactly. That's the picture of the proof. Right. Yeah, and so from here one could gain a bit more by doing book instead. So that's the first proof. So I think 10 minutes left, but I'd like to give you an idea of the second proof, which gives a slightly better constant, which is slightly strange. You take a little jump this way, and then take a big jump this way. Oops. This is K versus 9K over 10. And then you go down to like K over 5 versus 9K over 10.
What is this small jump?
Right. And this small jump is not using the book algorithm. It's using the very simple lemma that we used to do a big blue step. So this is expensive, but you actually win at, so if you do this argument, but instead for k versus L, you can do everything I just said, goes through exactly the same. You end up with picture just like this for any particular value of L. And actually, it's only when L is very close to k they overlap. If L is smaller, then actually these things miss each other. And so you win even up to, so it takes a little bit of work to do this, because you have to worry about the blue, off diagonal means we have to worry about the density at the beginning, right? We can't just say it's density a half. And so to get up to 9 over 10, actually we sort of do it in sort of 3 or 4 steps. But anyway, you can get there. And you win by some sort of, here you win by e to the k over 200 or something? K over 100? I forgot. Something like that. And this costs you something like just a tiny bit less than this. Right? So basically your jump costs you like, you're jumping distance k over 10, it costs you something like that squared. So it's actually like 1 over 100. And you win by a bit, and that's be fine.
So this walk in the scale world, you have like this density boost step that you can do so that you can get further when doing the book or something like this. Like a new density boost step. It's not density anymore.
Yeah, right. We want to just jump a bit off the diagonal, so that we win, so that the big book wins. Yeah. And when you're in between these two, the strategy is to walk towards the diagonal, taking single steps, until either your density is good enough to jump off, or you hit the diagonal, and then you say, okay, now we do the diagonal argument. Right. Or you get here. So how do we decide which way to jump here? This is the one with the higher density. Right? Yeah, you want to jump in the direction where you have density to half. And then you come here and you're like, okay, what's my density? Okay, I'm going to walk away until I get a good density, and then I do the step. Right? Sorry.
How do we choose the lengths of each step when we are far from the diagonal? Can we do this? Like in this algorithm, then we either did a large step, either win by another round.
Sorry, you mean? I mean, how do we know that we're in this range? Or
Yes, and so for this algorithm,
Yeah.
the picture is similar.
Yeah, right. So suppose you're here, and suppose you know your red density is what it's supposed to be. Okay, then you get a picture that looks just the same, except that's my light blue and pink, except these sets are smaller, and they don't intersect. Right? So wherever you don't know how big this is, so I don't know this is k over 5. This could, so I'm sort of lying here by saying this is k over 5. Wherever it is, you win. Doesn't matter where it is, right? Yeah, you just run it until it ends, and wherever it ends up, you know that Edis Sekera should be strong enough. Yeah. Yeah, in the worst case, like where these two sets are closest together is roughly at k at this point, right? So if you change n, make it smaller, these things move closer together, and the point at which they touch, that's where you know the worst case is. But yeah, at every stage you have a choice, right, of what to do. Like, suppose you're here. What density should you do the red book, and what density should you take another blue step? Right? It's not clear exactly how to optimize those two things. It depends on what bounds you've proved for the other Ramsey numbers. So in order to optimize this, presumably you have to say, okay, I've proved a bound for every particular Ramsey number. Now wherever I am, I say, okay, if the density is something, I take a step and I'd win the next guy. Or I can take the red book and win the worst case of this. You know, to compare those two things, that tells you what to do. And then I guess you update what numbers you have and can keep updating until it stabilizes. Right? We do some kind of Markov chain on Ramsey numbers. I don't know. Yeah, but this should all be done by a computer, right? This just gives you some explicit, fairly simple way of comparing Ramsey numbers, right? It's just this was diagonal, it's off diagonal, but you get off diagonal versus other off diagonal, and right. I mean, I guess the problem is it's against all off diagonal ones, right? You have to know this number for every value of t, or not know it. You have to have a list of bounds for every value of t. Yeah, but I mean, I assume that should be doable just by, yeah, right. Right. So that's probably enough for today. So maybe next time I'll try and tell you about the spheres conjecture. Okay. Yeah. Yeah, it's possible that I should wait a tiny bit because Julian is writing down a draft of the paper. So maybe I should wait a week. So it's possible that we skip a week. But anyway, so maybe on Wednesday I'll be ready to tell you. At least I maybe motivate it. Cool. Questions? All good? Cool. Okay, so maybe final class on Wednesday.